Everyone, good morning. So my research topic was advancing brain tumor detection in MRI images using neural networks. So for some background, brain cancer has a mortality rate of around 67%, meaning around 1 in 3 will survive brain cancer. One interesting statistic is that 77% of brain cancer is actually localized, which means that the masses don't spread and metastasize all over the body. This makes it much easier to target and remove masses. Usually this ends up in the form of benign brain tumors. Some existing advancements using artificial intelligence and machine learning are machine learning models to detect bone fractures. There are also models to find tumors and abnormal growths. And some problems with like brain cancer diagnosis and detection. Cancer in general is a time-sensitive disease, and brain cancer gets progressively worse and more aggressive as time goes on, meaning that MRI imaging and getting a diagnosis early is extremely important and crucial to treatment. So possible solution is using a program, a machine learning model, to recognize irregularities in MRI images to speed up a diagnosis. So computer science and machine learning has a lot of double meanings and terminology, so I just wanted to clear some up here. A tensor is like a matrix, which is a 2D grid, is shown in the first photo. Think of it like a cube. It can have n dimensions, or it can also be like the last image in the first image. It's like a set of cubes. It could be of any dimension, and it's just data stacked up. Pixel value is a numerical value of a color, or it could be a red, green, blue value, or a black and white value. And an image is essentially just a giant grid of all these pixel values, and that's how images are converted into numerical data to be analyzed. And finally, overfitting is a error, or more like a hindrance with the ML model. It's when it adheres a little too closely to the data and it starts to recognize images rather than patterns. That's not necessarily a good thing because it means it's not picking up on unseen data and it's adhering a little too close, and that can cause a lot of irregularities. As you can see in the third photo, overfitting is when you're trying to get a too good to be true kind of fit, and that's not always the most helpful. So machine learning is a computer science method and it involves statistics and calculus to make predictions. Predictions are based off of this concept that a prediction, which is z theta, is a parameter x times its weight or importance, w, plus any statistical bias, v. So you can see this equation here. An analogy I like to use for this is the peanut butter and jelly rule. If you have a peanut butter jelly sandwich and your friend tells you that it's too salty, do you increase the amount of jelly or decrease the amount of peanut butter? So both are completely valid options, and that's exactly what adjusting and a machine learning is adjusting all those parameters, which mean it would test increasing the amount of jelly and decreasing the amount of peanut butter and see which one gets a better result from your friend. And finally, why a convolutional neural network, or a CNN? It has exceptional grid processing abilities, and since images are large grids, a CNN is very well suited to this. So here's an overview of my methodology. Data pre-processing, which is just cleaning and ensuring the data is in order and ready to be analyzed. Neural network architecture, we designed this with 3 layers and a whole lot of other stuff that I'll go over. And finally, training, testing, and optimization. This is to ensure that the model is running to the best of its ability. So data pre-processing. I started by getting 5,712 brain tumor and no tumor training images. They're tumors of 3 types, the 3 most popular types, as you can see in the image. This is just some sample data. It's retrieved from a website called Kaggle, which hosts all these data sites and is really very much used in the data science world. And to pre-process this data, the first thing we did was remove this junk class called DS store, and this moves us into binary classification, which is just two classes. In this, the model is going to recognize no tumor or tumor, and that's it. So then to ensure that all the data is standardized, we rework the images, and finally data is loaded in batches of 128 images. Here's some code. If you can see the orange kind of rectangle, we see that the images are being transformed into 150 by 150, then it's horizontally flipped, then it's turned into a numerical tensor, and then those values are normalized, being within one standard deviation. So everything is somewhat like not too, the data is not too far. And you can see below in the last image that the batch size is 128 and shuffle is set to true, which just means that it's just the way to randomize data and avoid bias. Next, we built the architecture. We had a 3-layer architecture. 3 layers just means the input becomes the output 3 times. So the input was originally 3, which turns into 12, and then 12 turns into input, and so on and so forth. At the very end of the 3 layers, there are 32 feature maps, and to do all this feature mapping, we have kernels, which is kind of like a really small grid that is analyzing a big grid. You can see on the GIF on the right that a kernel is like the first box is like a bigger version of each grid. A smaller version of the massive grid, and it's taking select values. That's how the data gets smaller and smaller and smaller to analyze later. Batch normalization is once again just like making sure all the values are within one standard deviation, and it's going to stop some slow learning and like 2 small adjustments and 2 big adjustments known as vanishing or exploding gradients. Then we use the ReLU function, rectified linear unit, which is shown below. It outputs 0 for any negative values and x for any positive values. So you can see on the function on the it's a piecewise function. And this is just because real world data does not stray too far, and it's just it's a good representation of how the data is mapped. Max pooling is just a pooling layer. It's taking the largest numbers because the largest pixel values have kind of like a pattern to them. So like you can imagine like a tumor having maybe a lot of closer to 0 values, and it's recognizing those bigger values so that it knows that there's like a tumor there. The image above is what an architecture looks like. Conceptually, it's a convolution. You could see that it's scanning it, then it's making it into a smaller size data. It's convoluting it again and pooling, and then finally classifying. You can see here in the code, the first layer takes in 3 and outputs 12, and the second layer takes in 12 and outputs 20. The kernel size for this was a 3 by 3 for the regular and 2 by 2 for the max pooling. Finally, we get to training. Forward propagation is what I just mentioned. Output becomes input over and over again. And optimizers use RMS prop. It's taking partial derivatives, finding local extrema, and it's going to test in between them. So think of it as the first image where it's finding a local extrema, going up, and then realizing that's an upper bound, then going down, realizing that's a lower bound, and then fizzling out until it reaches an optimal point. And that's the most perfect the parameters can get. Lots of fluctuation, of course. Our loss function just quantifies the error for this. To quantify this one in particular, we used a logarithmic progression, meaning like a lot of loss means a near 0 probability. This is more accurate than like a straight line. Like a sloped line. And training epochs are just the number of times you want it to run. I tested this 2 separate times, once with a 10 epoch session and once with a 15 epoch session, and their loss training and validation accuracy are recorded. There we go. So you can see in the first image, that's a feed forward function. Input becomes output over and over again. And the left one is it's a very long function, but that's the train function. You can see the train functions being called, and all the images are being iterated through, and loss functions being recorded. And as mentioned before, I ran it 2 times. The best model is saved, and 50 pieces of unseen data out of the 1,000 pieces of unseen data are tested. It just chooses random 50 and results are recorded. As you can see to the left, to the right, there are multiple results. There's a lot more than that, but the green one shows an example of an accurate prediction. It's a no tumor, and it has resulted in a no tumor. But the red box shows an inaccurate false positive. It's a no tumor, but returned a tumor value. Here are my results. The total time for predictions for this is for the 15 epoch session. 60 seconds for 50 images. A very a big difference between a 1 to 2 week wait for the MRI results. An estimated accuracy of 86% for the 10 epoch session, and a final accuracy of 60% on the unseen data. Some notable trends: a very high number of false positives, and a lower accuracy rate for the 15 epoch session. So what happened? Why did it originally give 86%, but ended up resulting in 60%? Our guesses were it was lack of data preprocessing, and some overfitting, especially because there were a lot of false positives. That means the model was seeing stuff that was not there. So in that case, we think that overfitting and just analyzing patterns a little too closely could have caused all of these. Some possible improvements include color-related preprocessing, like grayscaling it and then increasing the contrast to make tumors more obvious. Transfer learning, which is training a submodel and then using that on bigger images. So in this case, that would entail training just with tumor images and then expanding that to big human brain MRI images. For the future, I hope that there'll be some improvements in accuracy, of course. Transformations with the least risk of error are used, and hopefully clinical use, where this can be used for patients to improve patient life and survival rate and expand towards other tumor types. To conclude, the purpose of this study was to find a model to identify and flag brain tumors to decrease MRI result time. The process included using the concepts of machine learning, data preprocessing, using 3 layers, a kernel scanning, pooling, and ReLU function, optimizing, training the model, testing on 50 pieces of unseen data, testing 2 times, once with 15 epochs, one with 10. My results included 86% training accuracy, 60% actual accuracy with a high false positive rate trend, likely a result of overfitting, but can be combated with color transformations and transfer learning. I just want to say thank you to my mentor. I don't think she could make it today, but I could not have done this without Dr. Khosravi, and to the amazing Talaria staff for making all this possible, and to my friends who helped me get through this.